Okay, let's talk a little bit more about the consequences of using groundwater. The groundwater aquifers, they need a recharge area. If you have an unconfined aquifer, the recharge area is going to be all the space above that aquifer. It's a little bit different for a confined aquifer in that there's an impervious layer on top of the aquifer, so the recharge area may be much smaller. When there is a loss of recharge area, it's usually related to land use changes. Usually there's some kind of impermeable cover put over the recharge area, whether it's buildings, asphalt, concrete, roads, sidewalks, parking lots, airports, compacted soil, just to name a few. And then there's also the act of channelizing that water that hits those impervious areas in an urbanized setting and sending that water through our storm sewer system versus letting that water infiltrate. Wetlands and floodplains are some of the biggest recharge areas for our groundwater supply. So paving floodplains or removing wetlands and filling them in, that decreases the recharge of the groundwater. What can be done then? What do we do? So planning ahead and creating less impervious surfaces. If there is a impervious surface and you can remove it, go for it. If there's a parking lot that's no longer used, don't be afraid. Just rip that thing out. Also putting in rain gardens. These days rain gardens are kind of cute. They're usually not very big. Having bigger rain gardens that are scattered community-wide would be an important way to get water back into the groundwater, and just less development and more preservation of wild spaces. Here's a hydrograph that shows the changes in the water table hydrograph. So this is not the river, this is the water table. And so we're looking at the height of the water table over time. The bottom graph is precipitation. So notice that when there is precipitation here in May and June, there are spikes, then the water table gets closer to the Earth's surface, right? The image here on the right shows two different conditions. The top condition is when there is abundant rainfall, and the bottom condition is after a dry period where you've got less water in the system, and so the stream level, the discharge in this little pockety stream here is way less than here at the high stream level when there's recharge in the aquifer and water flowing into that gaining stream. Here's two different places, two different times in the same place. On the left, Dr. Anderson is standing in hip-high water during the wet season, and then during the dry season on the right in the same location. Now the grass is green for sure, but there's no longer that standing water. Okay, so if we have natural ground cover, there's going to be infiltration of rainwater. There's evapotranspiration, the evaporation of water from the landscape and the transpiration of water out of the leaves of trees. There's going to be some runoff, and then there's going to be 25% deep infiltration. So 25 plus 25, that's the infiltration of water into the ground. Some of it's shallow, some of it's deep. 10% of the precipitation is runoff, and 40% of it is sent back into the atmosphere. If we then put on some impervious cover, so 75 to 100% impervious cover, we're looking at 15% of the water is going to get infiltrated and to become groundwater, either shallow or deep. 30% evapotranspiration, but 55% becomes runoff, running off of those impervious surfaces and mostly being sent into storm sewers. It has a negative impact on the stream channel. If we go way to the left, we're looking at a really small percentage of impervious surfaces, less than 5. In that case, the water is cool and clean, the stream banks are in good shape, Trout, which is a cold water species, is going to be happy. There's going to be lots of salamanders and mussels and insects. Adding into impervious surfaces makes the water warmer. Rainwater hits impervious surfaces, and before it runs off into the stream, it heats up on hot pavement. There may be some evidence of erosion. We lose our brookies. The brook trout are going to not be able to handle that fluctuation in temperature and the amount of sediment coming into the stream. Endangered species might be absent. We're going to bring in some more tolerant species like leeches, for heaven's sakes. We're going to lose some of our salamanders and our bugs. Adding in more 10 to 20%, we're going to have no trout. At this point, the water's too warm. Once you get to more than 20% impervious surfaces, then you're losing everything. You're only going to have left some really tolerant fish species, maybe some really tolerant bugs, and very few salamanders. So just looking at the image, where you want to be. You want to be here, you want to be here, here, or here. Pick your place, right, for the stream health. Recharge area of a confined aquifer. I mentioned how, so for a confined aquifer, that's the blue label, the blue colored aquifer here. It's not getting rain from above it, straight above it. The recharge area is way over here in the mountains, and it's a small recharge area. That water then flows into the aquifer. The artesian well that is dropped down into it is going to have water under pressure, and it's going to come out at that same level as the top of the water table in the recharge area. But if you were to cover that with impervious surface, you wouldn't have any more recharge. We use a lot of water in the United States of America. Whoops. We use a lot of water. Most of it is used for thermoelectric power. When I say use it, though, in that case, it's usually used in line just as a coolant. So it's used, but it's usually, other than maybe some heating of that water and maybe some thermal pollution, it goes straight back into the system and is usually pretty clean. The public supply, the irrigation, and the industrial, and the aquaculture, and the livestock, and the domestic, and the mining, those actually add in pollutants to the water. Okay, Ogallala. Ogallala is a huge aquifer in the breadbasket of America. It underlies lots of states: Nebraska, Kansas, Oklahoma, Colorado, Texas, Wyoming, South Dakota, and also a bit of New Mexico. It's called the Ogallala. That relates to the name of the formation, which is the mappable geological unit that is the Ogallala Formation. It's a sand and gravel aquifer that was shed off of the Rockies from the erosion of the Rockies. It's also called the High Plains Aquifer, and that encompasses other formations. So either term, though, is fine to use. It's the largest and most important agricultural area in the United States. Part of that is because we export 25% of our feed grain from there, 40% of wheat, flour, and cotton exports. So it's a big part of our international trade is the grains, food, cotton grown from Ogallala water. So it's left over from the melting Pleistocene ice sheet. Presently, there's basically no recharge. Any of the recharge that comes to the Ogallala Aquifer is very little rain, but then also from the water that is used in pumping out of the Ogallala, sprayed onto the fields, and then that water infiltrates and recharges a bit of the aquifer. This is what it looks like. Ogallala Aquifer. Here it is under a little bit of New Mexico, mostly Texas, Panhandle, Oklahoma, Kansas, Nebraska, South Dakota, Wyoming, a little bit of Colorado. And the big problem with the Ogallala Aquifer is that it's recharged by water that's polluted with agricultural chemicals. That's one. Number two is it is the water table is dropping and dropping and dropping. So this image shows the base of the Ogallala Aquifer. It's a cross section from the border between New Mexico and Texas over to the border between Texas and Oklahoma. So nearly right along the edge of the panhandle, this is what it looks like. Here's the ground surface. There is a topographical change. There's vertical exaggeration, just so you know, in this image. It's not quite that much relief there. But the land does drop down, and so does the Ogallala Aquifer. It's flowing from left to right. But over here in this purple region is showing just how much pumping is taking place out of the Ogallala Aquifer, and then the projected drop in the depth to the water table. So in this image on the left is saturated thickness. That's how thick is the aquifer. Notice that the thickest point is in the middle of Nebraska. So they're not experiencing a huge water level change in the middle of Nebraska. Other places here in the reds, more than 40 feet of water level change from the 80s into the 90s. So now we're in 2020, and now it's dropped way more than 40 feet. There are rivers that flow through the Ogallala Aquifer, so the thought is that one day the Ogallala water is going to get either too polluted or drop too far, too deep, and so maybe pulling water off of one of these other rivers like the North Platte, the Missouri, or the Red River would be a way to irrigate our breadbasket here. And it began as 3.3 billion acre-feet of water. In 1990, 15.6 million acre-feet were used for irrigation of 14 million acres of crops. In some places, the water table has dropped over 100 feet since 1940. The water could run out in a few decades. That's not that far from now. You will still be alive. Federal policies actually encourage the use of the Ogallala Aquifer through price supports and disaster payments and tax breaks. Farmers don't just make money. They get a ton of money from the federal government, and that's fine as long as it's done in a wise way. So what do you do in the future? You take water from the Mississippi, the Red, or the Arkansas rivers.